Go ahead and get started with our next speaker. His name is Vernon Asper, and he is a professor of marine science at the University of Southern Mississippi, where he has accumulated roughly 3 full years out at sea. Much of this has been through 19 trips to Antarctica, but an equal amount has also taken place in the Gulf of Mexico. He got his start in marine science through his fascination with the oceans and was inspired at an early age by watching Jacques Cousteau on TV and reading National Geographic. So working in an ocean-related field was a natural next step. He investigates the surrounding, his work included voyages of discovery in such places as the Arctic, the Black Sea, and the equatorial Pacific. His further investigations in the surrounding area have included numerous water sampling efforts, deployment of a time series collector for settling material, acquisitions of dozens of sediment samples, and deployment of a deep sea camera system that was used to document the existence of large aggregates of oil and other material throughout the water column. So Vernon will be speaking about the methods used to look for oil in situ. He'll also be discussing marine snow and oil. And his fun fact has to do with this picture. He built this airplane. So, pretty neat, huh? Yeah. So, without further ado, Vernon.
Okay, so the one question you're not allowed to ask is how long it took to build the airplane. Okay, 24 years, all right? So it took a long time, but it was worth it. A little bit more about who I am. I'm a professor of marine science. You told you about that. I am a gadget-minded person, so this is like the perfect venue for me to talk, because I just love anything technical. And the way I actually got into this study was I was involved in a project. Well, this is a little picture of me. Hang on, if I can get that. Nope. Hang on. This is worth it. This is one of my gadgets. That's actually me flying a boat. So that gives you an idea where my mind is in all of this stuff. No, that's not fun. That's work. This is a university-owned asset there, just in case you're wondering. Okay, so I got involved in this because I was involved in a consortium that studies natural seeps. There are lots of places in the Gulf of Mexico where oil and gas are coming out of the bottom of the ocean. Ian was involved even longer than I was. He'll talk about his work with oil in just a minute. But this is a little diagram of an observatory that we put in place in the Gulf of Mexico, and it had just about every sampling gadget and gizmo that you could think about to put on the bottom of the ocean in about 3,000 feet of water, 1,000 meters of water, to study oil and gas and hydrates and salt movement and seismics and just about anything else you could think about that goes on in the Gulf. We had one there. As an outgrowth of that project, I found myself operating this wonderful gadget. This is a robotic vehicle. Robotic means that it's autonomous. So you program this thing to do what you want it to do, you put it in the water, and 24 hours later it comes back, or doesn't, and it has data, or not, and you get pretty much what you get. So we were using this thing to do some mapping. It has a very high resolution multi-beam sonar on a swath mapping sonar. And by putting it right down near the sea floor in 1,000 meters of water or deeper, it can drive around and get super high resolution maps of the sea floor. And you can see all kinds of cool things if you can do that. So back in 2010, we were in the process of installing this vehicle on the research vessel Pelican. I'll show you a picture of that in a minute. And we were getting ready to go, and the oil spill happened. And we made a last-minute decision to just forget about mapping the seafloor and go and see what we could find out about the oil. So we took our AUV, autonomous undersea vehicle, off the deck. We put other gear on, and we went out to try and study the oil. Here's the Pelican. Now, we used every research vessel we could get our hands on. Mostly during the spill, NOAA vessels were not available because they were being used for the top secret response NERDA, they call it, work. We did use Walton Smith. We used the Endeavour, the Cape Hatteras, you name it. If it was available, we spent time on it. This is typical of the research vessels we use, in case you're not familiar with those. So is the Walton Smith. Most of them are either owned by the National Science Foundation or they're owned by the state that uses them. They're usually around 100 feet long. They've got laboratories, all kinds of things on board. This one happens to be operated out of Cocodrie, Louisiana by the Louisiana University Marine Consortium. And it's known for having an unusually good ride for its length. It's about 100 feet, 15 feet long, and it's known for having exquisitely good food. They have extremely high standards down there in Cajun country, so the food is always really good. So as you can see, this was during the spill. We went out there to see where the oil was going, and we wanted to know specifically what was happening to all of this oil. Where was it going? Was it being dispersed? Was it being collected? Was it being moved away by the winds? Was it sinking? What was going on? So when we were on the way out there, we had heard on the news, because that was our best source of information at the time, we heard that they had decided to start putting a dispersant into the flow of oil as it was coming out of the well, with the intent of keeping the oil dispersed at depth and from getting to the surface. And we said, can they do that? We don't know. Nobody had ever really done it before on that scale. So we said, well, let's get the best equipment we can, and let's try to see if we can find any oil down there, down in the water that's not getting to the surface. Keep in mind that in those days, the mindset was oil floats. So if oil gets into the water, you're going to find it at the surface, period. It doesn't get to the sea floor, it doesn't make a plume, it doesn't do any of that stuff. So we got this gadget right here. This is called a fluorometer, and just in case you're not familiar with fluorometers, let me tell you a little bit how they work. The phenomenon of fluorescence is that if you shine light on an object of specific properties, it will shine back at you with a different color light. For those of us who grew up in the 60s, we had these fluorescent posters with black light that we put on the walls, and they were all psychedelic and everything. Okay, I'm dating myself, I guess. But that's the process. The black light is ultraviolet light. It hits these paints on the poster and would shine, glow these wild colors. Well, it turns out that many compounds in nature do exactly the same thing. Oil's one of them. So if you hit oil with blue or near ultraviolet light, it will fluoresce back in different colors. And this little diagram here shows different kinds of oil and what color they will show up if you hit them with ultraviolet light. So we got this fluorometer, this gadget right here, and we put it on this package. You can see it right down there. Or we put it on this little tow-yo gadget, and we would either lower it down to the bottom and bring it back up so we could see the whole water column, or we would tow it along the surface and see the oil near the surface. And we got all kinds of cool results. We did a bunch of surveys here on all of these stations here. This is a typical profile that shows this is what is called CDOM voltage. Don't worry about that. But this is the actual amount of what we interpreted as oil at those depths, because what else would be down there? This is 1,000, 1,100 meters or so. And there's not much else that's going to be down there fluorescing. There just isn't. So we said, well, it must be oil, and we communicated those results. We submitted a paper for publication that showed actually several layers of oil down there, not just the one at 1,200, but there were actually several layers at that time. And we were the very first people on site doing this. After we were out there, of course, a lot of other people said, hey, that's a pretty neat technique, and they started doing it as well, which we were kind of thrilled with. If you want to get really, really serious about using this fluorescence method to understand oil, one of the things you can do is, instead of just using one color of light like my primitive little $7,000 fluorometer would do, in the laboratory, you can use a whole variety of wavelengths. And this gadget here uses a different sequence of emission, different wavelengths of light, and then it looks for what comes, different wavelengths of light for excitation. We excite the oil with this light, and we look at the light that's emitted. And by looking at what a given compound responds, if you hit it with this color of light, if it responds that color, you can sort of fingerprint, not really accurately, but you get a really good idea of what compounds of oil are down there. This is an amazing technique. Unfortunately, nobody does it underwater yet. So if you want to do this, you've got to take a sample of oil in the water, take it back to the laboratory, and do your analysis there. You get it after the fact, which is just fine. If you want to get even more serious about it, you can use a gas chromatograph. This is the standard technique. A gas chromatograph takes oil in water, and it runs it through a column which has a resin inside it, and so the oil will stick to the resin and then pop off and stick and pop off, and depending on its molecular weight and how many carbon atoms it has, it'll come out the other end of the column sooner if it's smaller, or later if it's bigger, depending on its properties, and you get a spectrum that kind of looks like that. That's pretty cool. And if you want to know more about the specific molecules, you can take a gadget like this, a mass spectrometer. Mass spectrometer is a very, very complicated equipment, and it uses high vacuum and an ion gun to take the compounds that you're giving it, accelerates them in a vacuum, and then makes them go around a real sharp bend. Well, the little ones, the low molecular weight, the lightweight molecules will make it around the bend. The big ones, not so much. They slide off and hit the wall. So if you look at where they splatter on the wall, you can look at their molecular weight. So that's called a mass spectrometer because it spreads them out according to their mass. And there it is. This cannot be put underwater. There's just no way. Unless you're this guy right here. This is Rich Camilli. He was mentioned earlier. And he actually helped develop a mass spectrometer that goes underwater. I mean, this is like the craziest thing you could ever imagine because it's so hard to do. But other people have tried and other people have had various degrees of success. But Rich Camilli, that's his claim to fame. He developed it. This is it. It looks like a little bomb because it's in a pressure housing. And this guy here, Dana Yorger, brought out Sentry. Monica, I think, mentioned Sentry in her introduction. Sentry is an autonomous vehicle robot, just like the one we used, only Sentry is built specifically to do this sort of thing. And it's highly maneuverable. It's a lot slower than ours, but it's highly maneuverable, does a lot of cool things. So they brought this mass spec, Tethys, and they put it on Sentry, and they brought it into the Gulf, and Monica showed the little animation showing how they found things, and they actually went back and confirmed the plume that we had reported, and they went one step beyond, and they said, okay, those guys thought it was oil. It turns out it is oil. And not only is it oil, but we'll tell you about what various compounds are in there, and we're pretty sure that this is coming out of the Deepwater Horizon. So we use a very simple technology, a single wavelength fluorometer, to say, yeah, there's oil down there, we're pretty sure. These guys went out and said, okay, we'll be specific. So this technique is one of the state-of-the-art techniques. So then you might say, well, what happens to this oil that's on the surface? What happens to the oil that's down there in that plume? Where's it going to go? We don't have an ROV like the one that was shown with the sperm whale. What we have is this cute little video ray ROV. So we put that in the water, and you can see there's no oil on the surface, but down below the surface, there are all of these big aggregates. Sometimes people call it sea snot, they call it all kinds of things. We call it marine snow because that's a lot more picturesque than some of the other things that it's called. But look at this stuff. There were these big globs of orange-brown looking stuff under the surface of the water. Wait a minute, oil floats. What's it doing under the surface of the water? Well, if it got that deep, could it go deeper? Well, we had to find out, so we brought out a piece of technology that was designed back in the 80s to study marine snow, and it's just a simple camera system. There's a collimated light source over here and a camera that lays on here. Here's the camera, there's the light source. So anything between these two strobe lights is going to be lit up. Anything in here is not going to be lit up. Anything over here is not going to be lit up. So we took this out on the Walton Smith, as a matter of fact, and we lowered it down to and then through this plume of oil. And here's some pictures. I'm not sure how well you can, not bad. This is a picture taken at about 400 meters, and you can see these little dots. That's why we call it marine snow. Doesn't it look like snow? Sort of? Yeah, okay. Get down a little bit deeper, just above this plume, and now we're starting to see this stuff. This is not normal. This is something we never saw anywhere else before this time. Getting down into the plume now, and you can see more and more of these particles further into the plume, and it just turns like a milkshake. There was so much stuff in the water that you really couldn't say what was going on. And then down below it, you see more of this marine snow, only it's larger, and instead of being orange, it's white. So it looks like some of the oil in this plume is rising, and some of it is hanging out there, and some of it's sinking. So then you say, well, how are you going to find out what's rising and falling? This is some of the data. I don't have numbers on this plot simply because the numbers were so high that nobody would believe them, including me. So these are total volumes and counts per liter, and nobody really knows. Okay, so how are you going to find out if the water is sinking? The easiest way to do that is to take some instruments and put them on a mooring, a permanent mooring in the ocean, and let these particles settle into it. So this is a mooring. Here's the bottom. Let's say that the bottom is at 1,500 meters. It rises up off the bottom only 120 meters. So all of this instrumentation is hanging near the bottom, and that's important because I'll mention later, near the bottom, and particles are going to be settling into it. This is a typical what we call sediment trap. So particles fall into it and they go into one of those little cups and then it rotates around and we get a time series sample of the stuff that's falling in there. Did we find oil in there? Absolutely, but only while the oil was still flowing. Very quickly after that, we didn't see a lot of oil in there. We also had this little camera here, gadget here. This was designed to look at sinking marine snow, and here's how it works. This is the picture of it. Does it look like it was built by a graduate student? It was. They do all the real work, of course. And what it consists of is a clear box with a settling tube. Particles fall down this tube into this box, and this camera with this strobe takes pictures of them. Here is the camera. This is just after recovery. It's got condensation over it because it was down in the cold. And here's the box. Now let's take the lid off and look down inside there, and you can see the particles that fell down there. And that camera photographs them as they sink, and so you actually get a time series sample of them as they sink, and you can measure sinking speeds. That's really important. So do they sink? Well, here is a video of them. This is what it normally looks like, and you're going to see the number of things of snowflakes in there increase dramatically. This is the most snow we have ever seen anywhere in the ocean. And so we call this our underwater snowstorm. And this is this was just after Hurricane Isaac, by the way. And it turns out that this is the current meter that was on the mooring also. And if you look here, right here is where Hurricane Isaac passed, and right here is this big snowstorm. And you can see very high flows, and you can see this is the strength of the echo in this current meter. The current meter is an acoustic current meter, uses sound, so the strength of the echo gives you that. It turns out that that snowstorm was stuff that was resuspended from the bottom. So apparently Hurricane Isaac went by, churned things all up, moved them around, and they settled out into that camera system. So not only does the snow get the oil to the bottom, but it also gets it, moves it around on occasion. And I want to show you one more little technique, because my time is up, and this is CODAR. This is not very glamorous, but it's one of the most useful pieces of equipment that we have. This is a high-frequency, solid-state radar system, and this antenna is the only part basically to it aside from an electronic box. No moving parts, solid state. Looks over the horizon, looks at the Doppler shift of echoes coming back from waves, and measures surface currents. So here's a little animation showing what the surface currents were. This was actually before the oil spill, but the oil spill was out in here. And for the oil that was getting up onto the shelf, we had a pretty good idea where it was going and what the currents were doing to it because we had live radar showing those flows. So, summary, amazing technology. Everybody knows the movie this is from, right? Okay. Technology rocks. I just love gadgets, and the gadgets keep getting better and better, and for many of them, we're getting cheaper and cheaper, so we're able to afford them. We've learned more about the Gulf of Mexico through these studies and through this technology that's available than we ever had before. So in one case, it's sort of the funding anyway is sort of a godsend for us. Okay.
Sorry, for this section, I forgot to mention, we're going to hold off on questions until all three of our speakers go, and then we'll bring them back up to the panel. And if you have questions, write them down now, and we'll go back to questions after all three of our speakers. So, thank you, Vernon.
Okay.